Okay. How do you calculate the atomic mass of carbon given the atomic mass of the stable isotopes? So how to calculate atomic, so AMU of carbon given the atomic mass of stable isotopes. So that's honestly a great question, but this is actually what's even done in real life. So the thing is that finding carbon that's 12.011 or whatever it is, let's see here, yep, 12.011 grams in nature, that's almost that doesn't really exist like that. The reason why I say that is because each based on how they calculated the moles and everything else, you would typically have it to where for every, I guess if this makes sense, for every mole of a proton, it's around 1 gram. Okay, and the reason why I say every mole of proton is because think of hydrogen is actually a perfect example. Most of the times it's run around with just H plus, and you notice that its preferred state is just like 1 gram almost, like you see 1.008. That's around the mole of a proton, and neutrons equal around there too. A mole of a neutron will be around 1 gram in terms of that'd be the molar mass, gram per mole of neutron and proton. Now knowing this though is because when you have like carbon and stuff, right, they don't have a half amount of proton or half amount of neutrons and stuff like that. They have full-on neutrons, full-on protons. So you find that in nature, right, you'll see things like this where it's like carbon, where it just means like carbon 12, meaning that technically this would weigh just 12 grams. Okay, and that's because it has 6 protons, and you probably guess you have to subtract the 12 from the 6, and that's the amount of neutrons you'd have. So to have this carbon will have 6 protons, 6 neutrons. Okay, but there are also carbons running around nature that are like 13.6. Okay, still carbon, right? But now it has 6 protons, 7 neutrons, and this 13 here relative to that 12 there means that this carbon actually weighs around 13 grams. Now these are just carbons that do appear in nature, okay? But in terms of now to calculate the atomic mass, right, they appear in percentages. So let's say out of the 100% of carbons out there, the reason you have a number so close to 12 is because typically you see like around 90, a really high number, 96, 98, something like that. 98% of carbons are the 12.6, and like 2% of the carbons are 13.6. So the way you calculate the atomic mass unit is because is by getting this mass here and multiplying it by the percentage that shows up, because it's pretty much saying now that the 12 grams accounts for 98% of all the carbons out there, and the 13 grams counts for like the 2% there. And you notice that you end up getting a number that's a little bit greater than 12. So like in this example here, I'm using 98 and 2, so it'd be like 12 grams times 0.98 plus 13 grams times 0.02, because remember this is percentages, so it's going to be whatever number you get divided by 100, which is why we have 0.98 and 0.02. When I put that in my calculator, plus 13 times 0.02, you actually get 12.02. That is how they actually got the atomic mass. So when you see these numbers on your periodic table, that is actually all all the recorded common isotopes of that element added together in these percentages based on the percentage of how much they account for. Okay, and that's how they get their actual atomic mass you see on the periodic table. So that would be how you calculate it. As they see here, they actually use what's been shown like on record, like the empirical data, and there's exactly a lot close to like almost 99% of carbon 12. I mean, of carbon is carbon 12, and only the 1% is that stranger carbon 13. And think of it this way: there are actually different types of isotopes as well, like even maybe carbon 14 or carbon 11, like those really rare ones. Only the ones that they're actually shown that can actually exist. But the point being though is that they're like less than 0.1%. For example, they account for so little of it that it barely changes or even doesn't change the atomic mass of that element. When you get to bigger elements like uranium and stuff, for example, they have a lot of isotopes, very unstable isotopes, but nonetheless still there. And because they're there, they're factored in, but the percentage of how they exist in nature makes them not affect the total atomic mass as much. But yeah, so this is correct. So let's submit that. Now let's move on to question 6 now.